Hello everyone, and welcome to our next educational video in our series on electricity in HET. So last week we talked about the strength of an electric field, how to measure that. Which is E equals Coulomb's constant times the charge all over R squared, which is measured in newtons per Coulomb. Now, this week we're going to be talking about the electric potential, also known as voltage, which is measured in volts. So now this voltage, another way of saying it is the change in potential energy. So this U here denotes potential energy, which is measured in joules. That will come into effect later. Per unit of charge, Q. So potential energy, or I should say rather the change in potential. So this is how we write change in math speak, because there's a little triangle here. Per unit of charge. Okay. So to better get an idea of, the whole potential energy concept, so I'm a mechanical engineer, but for those of you who are watching this video might not be as in tune with this, we're going to look at an example from gravity. So when we're talking about potential energy in terms of gravity, we have the potential energy is going to be equal to the mass times the acceleration of gravity, which here is 9.81 meters per second squared, times our height. So let's say that we have, a ball up here. Okay, and this ball is at a height h equals 2 meters, and this ball has a mass of 2.3 kilograms. Okay, so this is our floor right here. Okay, so then at the bottom, h would equal 0. All right, so our potential energy is going to be equal to our 2.3 kilograms times our acceleration of gravity, the 9.81 meters per second squared, times our height of 2 meters. Okay, so that all boils down to our ball here, when calculated, has a potential energy of 45.126 joules. So potential energy, again, is measured in joules. So that's the potential energy when the ball is at this height of 2 meters here. So now when the ball is at the floor here, so let's say we drop this ball. At this point here, once it hits the floor, it doesn't have any more potential energy anymore. There's no, like, this ball can't drop any further. But, you know, the first law of thermodynamics says that energy can't be either created or destroyed. So we know that that energy has to go somewhere, which it would be into kinetic energy. So kinetic energy, KE, is going to be equal to the same as what we had before, right? It's all, at this point, all of our potential energy has been converted into kinetic energy. It's equal to 45.126 joules. And our equation for kinetic energy is going to be 1/2 mv squared. So using this equation, so we know the mass of our ball here. That's our 2.3 kilograms. All right, and we know our kinetic energy number. So from that, we can actually find out how fast this ball is moving once it hits the floor. So to do that, we have our 45.126 joules is equal to 1/2 2.3 kilograms v squared, which when we rearrange this equation, we find that our velocity is going to be equal to the square root of 2 times 45.126 joules all over 2.3 kilograms. Okay, which comes out to 6.264 meters per second. All right, but basically, so main thing to get out of this is that potential energy is stored energy right? So if we lift this ball, we're effectively storing energy by means of gravity. So it's stored energy that has the potential engineers and physicists aren't the most creative individuals. So it has the potential to be transformed into another kind of energy. So here in this example, we used gravity to store potential energy that was then created into kinetic energy when we drop the ball. So here, when we drop the ball here, our velocity is going to be equal to 0, so we got no kinetic energy. And then all of that is converted into kinetic energy by the time that the ball hits the floor, at which point our ball is moving at a velocity of 6.264 meters per second. Okay, so then how does this relate to electricity? Well, so electric potential or voltage is also strongly related to the electric potential energy. Let's see if our Sharpie makes it through this. Sorry, electric potential energy. So for this example, we're going to kind of go back to our foil experiment where, you know, we used static electricity to induce a polarity on the foil where all of the charge on one side of the foil was positively charged, all the charge on the other side was negatively charged. So in this example, we're basically going to have two plates that are infinitely large. One of these plates is going to be positive, one of these is going to be negative, and then we're going to have a charge somewhere in the middle. So we got two infinitely large plates. Or charge plates, I should say. And this is going to create a uniform electric field. So if we draw a whole bunch of positive charges over here, 1, 2, 3, 4, 5, and these just go on forever in either direction. And then on the opposite side we have negative charges. Which go forever in each direction. But so basically each of these charges has a field line associated with it. And because we have an equal amount of charges and these are infinitely large, all these field lines are just going to go directly to the right. So they're going out from the positive to the negative. And this goes on for infinity in that direction, on for infinity in that direction. But so we're going to pretend that these are evenly spaced. Because these are evenly spaced, we can see, from drawing like a circle, if these circles are the same size, we're always going to have the same charge density no matter where we draw this circle. So like I said before, we have a uniform electric field, and that electric field is going to be equal in this case to 5 newtons per coulomb. That's going to kind of be like our imaginary number that we're going with. And this distance here between the plates is going to have a length of 3 meters. So let's say that we have a proton in the middle of this field. So we're going to draw our proton here. And he's at, a distance here of, say 1.5 meters. So he's in the midpoint. Okay. So our energy, or let's say work, because work is measured in units of energy, is going to be equal to force over a distance. So we know our distance here is equal to 1.5 meters. So to get the electric potential energy, we're going to measure the force that is applied over this distance here, and multiply that to find out exactly what the change in energy is. So here we're going to have some potential energy by the, when our proton is here stationary, but it's in an electric field, so it wants to move this way. But then by the time it reaches, these negative charges over here, it's not going to have any potential energy anymore. So at that point, our energy would be fully converted. All right, so our force, and this force is going to be the same no matter where we are in the field. So we're going to find that it's equal to E, which is constant, right? It's uniform field, times our charge. And this charge is never changing. It's always going to be 1.6 times 10 negative 19th coulombs. Although we're going to find out that this number doesn't really actually matter. Since here, so we have our field, which is going to be measured in newtons per coulomb, and our Q here is going to be coulombs. So these coulombs cancel, which leaves us with newtons, which is what we expect because we're trying to measure the force. So anyway, we were going to measure, let's say we're trying to measure the voltage here, so V, which is, the change in potential, which is what we're trying to calculate here, over the charge Q. So this can be rewritten as, force times our change in distance, right? Because we have to have a change here. So that's where that change goes, over Q, which is going to be equal to E Q delta D over Q. So the voltage in this situation, whatever our charge is here, doesn't matter as far as voltage is concerned, because these Q's here are going to cancel. So we're really only concerned with the strength of the field times the change in distance here. So we can say that, from here to here, the voltage is going to be whatever the field is times the change in distance. So here, if we wanted to calculate, what's the voltage between this point here, and this plate, we would say that the voltage is equal to our field, 5 newtons per coulomb, times 1.5 meters minus 0 meters, right? Because we're calculating the change. So this is our delta D. That don't need to worry about him. So our voltage is equal to 7.5 volts from this point to this point. So now if we were to try to measure the voltage across you know, the entire length here from, you know, from the positive plate to the negative plate, that would be equal to 5 newtons per coulomb times 3 meters. 3.0 meters minus 0 meters. Which would be equal to 15 volts, right? Which is what we expect because it's twice the distance, so we got twice the voltage. Okay. So now what does this all imply here? So again, so no matter what this charge is, the voltage that it experiences isn't going to be due to the, you know, the amount of charge at all. It's just going to be due to the field that it's in. Now, the force that this thing feels is going to change based on, you know, how big this is and what, you know, the charge is. Because we can see here that, you know, the force is going to be equal, you know, to the strength of the field times the magnitude of this charge here. So, and this is where, you know, if we were trying to calculate, you know, what the speed of this proton is here, we would then need to know the magnitude of this charge and what the mass of this proton is. Since that would, you know, then we're talking about, you know, in terms of, you know, energy, not voltage. But voltage takes charge kind of like out of the equation. It's basically saying, you know, like how much energy, you know, per charge do you have, or how hard are you pushing charge through this field. And we'll get into this a little bit more in depth next week when we talk about batteries. But until then, you know, thanks for, you know, sticking with me this long. I hope you like this video. Remember to subscribe. And again, we'll see you next week.